sir, but not looking at the nadir. Nadir means it's not looking at the 0 degree, because for any getting any distance, you need like to see the exact down, that means the 0 degree or nadir. Spectrometer is the sensor which looks at another angle, maybe a 30-40 degree. Depending on that what type of function was. Generally, we take 30 to 60 degree angle it sees, and from that it get back scatter. That means scattering all this energy, whatever you send the energy, like suppose you send the energy x, then 0.5x or 0.4x, depending upon the what type of targets are there or what type of information is there, how target is oriented toward your uh, sensor. So all those things it takes in common. So by that it gives the takes back the energy, and then you get that information. This is a sensor mainly used for the ocean surface wind. That is from the surface. Through that, actually, this is very important information for the point of view. We say the numerical weather prediction. Whether you get all this information about the weather, and then how you predict it for the long 3 days, 5 days. For that, you need this information to assimilate in the model. So those are actually more details. I will not go about that. So this is another type of sensor. And third sensor is synthetic aperture radar. This is the sensor similar to the spectrometer, I can say, but it is very, very high resolution. Resolution I will come upon. That means very, very fine information you can get. That basically, you can say the very, very fine information, detailed information in respect to all other sensors you are getting in the microwave region. So this synthetic aperture radar, as name says. And another optical is also one sensor is there, active sensor called LiDAR, similar to the synthetic aperture radar, that is optical. So these are some of the sensor, passive as well as active sensors, what we call it. Yes, when I was talking about it, how do you get the information? That means you are having the radiation either from the sun, so that is you are getting, or from the active sensor, you are sending some information through radars. That radiation will be having interaction with the medium itself. Medium, I means to say atmosphere. Whatever in, because your satellite is almost some are the 800 kilometer of 1,000 kilometers, some are 36,000 kilometers, like geostationary. So when the signal is coming, and signal has to interact with the medium, because there is some medium. There are different type of gases are there in the atmosphere. So there will be absorption will be there, emission will be there, what we call it, attenuation will be there. So that interaction will be there, which will depend upon the what frequency or wavelength we are talking about. Because these sensors work, as I was told previously itself, from the optical 0.4 to 0.7 micron to the 100 centimeter in the microwave. So depending on the what type of frequency is there, your the size of your particles or different atmosphere constituents are there. So it will have a interaction. Depend upon that, many other things like polarization, angle. There are many other things are also there. Based on that, you have the interaction from the matter, what we call it, as well as your incident radiation. Due to that only, because of these different phenomena, you get the information about the or different constituents, and you get the classify different things on the surface of the earth, as well as that things on the surface of the earth, as well as the atmosphere. So as this cartoon shows, in the energy is there in the terms of the sun, and it is coming to the earth surface, and then at particular angle it is going. As you know, you might have read about Snell's law, all those things also. If its surface is very, very smooth, that means flat surface, it will have angle of incidence, the angle will be same. But if their surface is not smooth, rough, then angle will be different, it will be going some other place. So by that, basically through this phenomena, you are having the energy getting to the systems or your satellite system. And in that, in between, there is transmission I was talking about, because you are getting energy from a system, so the transmission will be there. Then some absorption will be there from the atmosphere itself, will be some absorption will be there based on the constituent, based on the gas, as well as the absorption when it's reaching to the surface of the earth, land as well as the ocean. Even then also there is some absorption of energy, what we are getting will be there. And in addition to the absorption, there will be emission also, because at different wavelengths, energy will be emitted differently. So emission is there, one of the phenomena. Then scattering, as I was talking, all the energy what we are getting in the sensor, that will be scattered back. Part of that energy will be scattered back also. And reflection. So all those phenomena takes into account when we are talking about that information content, what we derive from the satellite data or using the sensors based on the any particular satellite or any particular information. So basics of telling these things is you can understand now. When we say I am able to identify particular type of crop by seeing the eye directly, if I go to near to the any field, I can identify based on my experience, because that also goes on experience. I can say this is the wheat, this is the rice, a particular type of rice, particular growth is there. But if you are seeing from the 800 kilometers away, and in between, so many phenomena are also taken into account. So how difficult it will be there to get this classification as well as the information content generation based on all those phenomena, all those physics, as well as the vertical related transfer equations we solve, and other training things, and as well as the other data what we collect, because of when we want to classify anything, we need the other data also. Not only this information itself is not sufficient. So based on all those things, we get this information. So anyhow, we discussed this thing. One is we get the information. Earlier we used to get the aerial photography, that is also remote sensing. And but this is cannot go to the very large scale. Only the at particular time you having a few kilometers only, and anyhow, the 3 to 4 hour flight if you go, you will get some data, and then processing of data, storage of data, all those many issues are there in the when we go to the aerial remote sensing. But advantage is there, you can fly very near to the surface of 6 kilometer, 8 kilometer also, based on the what type of sensor, what type of information you want, and anytime you can go to the place. For the testing of instrument, mainly for the if any instrument or any sensor when we developed, we go accordingly what type of information we should be there, what type of sensor should be there. So accordingly we make that test those sensors. And anyhow, satellite remote sensing, what we are talking based on the different type of satellites. Yeah, then satellites, there are two types of basically what we will be talking about, the two types of orbits. One is geostationary orbits. Geostationary means it is seeing same place all the time. That means the orbit is around 36,000 kilometer orbit is there. We are not going much detail into that, but it can be solved by the equations. We can see around when it is around that height, then with the spin of the Earth as well as the spin of the satellite, both are exactly same orbit. So because of that, you are seeing almost the same area all the time. And this type of orbits are basically used for the weather satellite. That means for seeing the atmosphere phenomena. So, and another type of orbits are the polar orbiting or geosynchronous satellites. They are orbiting all over the world from the mostly, I can say, pole to pole, approximately pole to pole. And the orbit is around 100 meters, in around 100 minutes. It covers that one orbit, and then it by the time your Earth is also moving, so you will cover another area. Like that, it goes on covering the whole Earth in approximately depends upon the sometime is 2 days, 5 days, 10 days. What type of orbits are there? What type of precision is there, and many other things, and what type of your requirement. Based on that, we have a different orbits in the polar orbits. There are many other orbits are there, what you call the geosynchronous orbits are there, Molniya orbit are there, very, very highly elliptical orbit, which are basically for this purpose of the seeing the high latitude regions. So, but mostly we use the geostationary and polar orbit satellite for that. This is one of the picture taken from web only. This is aerial photography. Very clearly, you can see the very, very fine information from the any aerial photograph. And this is one picture from the satellite image of our own satellite, high resolution. This is Hyderabad only. You can say Sensagal Lake and airport. So based on the resolution and all those spectral range, we get a different type of information. In the sensor point of view, what we call it, I will coming about the resolution also, but overall area what sensor sees is what we call the field of view, FOV what we call it. At a particular time, total area, how much is seen the field of view. And in each sensor also, there may be many detectors, like 30, 40 detectors are there. Each detector will be seeing one particular area. That is called instantaneous field of view, or we call it IOV. So that is the basics of how you get that information about very, very fine information based on the what type of detectors you are having. And each sensors, we can have suppose 4 sensor, 10 sensor, or 20 sensor. Each sensor will be go on taking information at particular point of the Earth. The sensors are adjusted like that for the same point on the Earth. You get the information from the different channels or the spectral bands. Like in this case, we are showing from the red band, green band, blue band, and infrared bands. And then all this information for all these pixels, for pixel means each point, what we call it, and the scan line, that's why you get the whole image. So based on that, you get the total area and the information about that. I will be coming later on in detail. For each pixel, how you get the different type of information. That is basically because of this. For suppose like this sensor, for first point, you are seeing the red band in 0, second is 2, green band 10 and 12, blue band 20. So if I process accordingly, if I see in the blue band only, then I will get particular information. If I combine blue and green, then I get different form. So this way, we select the sensor accordingly also what type of information we want to generate, and when we want to classify or derive the information, that type we use choose those bands. So, and remote sensing, one thing is basically comes with the resolution. The resolution are the basically of the 4 types. One is spatial resolution, that means the area wise, what we are seeing, the smallest area what we can see or detect from any particular sensors. Some of you might have heard of also what you call the 0.2 meter resolution, 0.5 meter resolution, 1 meter resolution, 10 kilometer resolution. So those are the means. A 10 kilometer resolution means you cannot resolve the information less than 10 kilometer by 10 kilometer. That is approximately, if you see 10 kilometer, 10 kilometers are approximately 100 square kilometer. Similarly, for 1 meter resolution, you can take an area 1 meter by 1 meter. Basically, exactly it is not 1 meter, 1 meter, because if you plot the overall histogram, there will be some 3 dB bandwidth will be there. So, but approximately it says 1 meter means less than 1 meter information you cannot derive with very high accuracy. So that is a resolution, what we call it, a spatial resolution. Then comes the spectral resolution. That means how many spectral bands you are having. Like I was earlier slide, I was talking about that red, green, infrared. So what type of spectral, like 0.4 nanometer to 0.4 to 0.45 or 0.4 to 0.41 only I am having. So based on that, what type of spectral information I want or what type of sensors I can make. So those are the spectral resolution. That means one line in the spectroscopy you might have learned that line width we call it. So for any channel, particular spectral line will be there, and around that you can make the channel broadband or the very narrow channels. So that's called the spectral resolution. Then third is the radiometric resolution. That means how many digit or bits you want to get the information. You get 2 bit, 4 bit, 8 bit, 10 bit. So that is called the radiometric resolution. That is also depend upon how much information you want and how much information you can store in the satellite, because satellite or sensor also are limited by the total systems storage also. It cannot go on storing because it has to download at some place. That's called it the ground stations, different ground stations on the globe. All the country have their own, and with cooperation they use the others also. So based on all this information, when you are seeing from satellite any ground station, then only you can download that data whatever has been gathered. So based on all those things, radio resolution is also defined accordingly. And then fourth one is the actually temporal resolution. Temporal resolution means how after how much time that particular information or particular area is being covered. As I told, some like geostationary satellite is seeing every 5 minutes, 10 minutes, or half an hour, 1 hour, the same area, because it is at same place. So it can see at very, very fine temporal resolution. But it is orbital, like polar orbit satellites, they come sometime in 2 days, 4 days, 8 days, like that. Like IIRS for 23 days, 25 days, some are there. So this is called the temporal resolution. So our information generation, we need to keep in mind all those resolution also, because the sensor will be developed accordingly, and because the complexity also increase when we in the sensor wise as well as your satellite wise, all those things. This is one example of resolution. We just can see left hand side is 0.5 by 0.5 meter, and this is 2 meter. So 0.5 meter to the 10 meter, if you see all these images, then you can understand 0.5 meter you can see very, very fine resolution information. But in 10 meter, all this information, same information, we are just averaging to showcase. It is not from the different satellite has been taken, but suppose you take 0.5 meter versus a 10 meter. 10 meter, you can see those information very clearly. So that is advantage of resolution. But is the disadvantage when you go to very, very high resolution of this type, you need a very high storage as well as data download, and sensor also should be of that quality. And then so that's why based on the, I know you don't require for the very, very high resolution for each and everything. For cartography type of purpose, we require very, very high resolution. Otherwise, we can go for the 5 meter, 10 meter, depending on the. And these are the different resolution as well as the different spectral also. Like first case, we are talking 0.6 meter resolution, which is our own cartoset, what we call it. Then 1 meter, this is and the right hand side cartoset to 1.6 meter. So there are different channels are there. They are having different resolution. Like what is 0.5 meter is there pan as well as 2 meter. Suppose it is there your spectral channel. You can combine those things also. That means both the information, you can take advantage of both the information, high resolution, but in one channel only, or one color, what we call it, black and white. But a different colors information, but it's not very high spectral resolution. So by combining those things, also we get various type of information. So this is one examples of that how we get different channel information, and from that, starting from that, we have up to the 56 meters, 72 56 meters AWIPS data, what is called advanced wide field sensor, then 72 meter, like that, different type of information for the large scale information, which is not changing very frequently, and especially also for that we don't need very high resolution, but we get the larger swath means total area, how much we can cover. So based on that, these are different resolutions are there. Spectral resolution, as I was talking about, basically if you see spectral resolution, what we call it is a black and white image. Black and then a blue, green, red. Basically 3 colors. Everything, all colors are made. So 0.4 to 0.7, if you have the only one color, so that is a black and white image you get. But based on 3 colors, all these things, you can see the peaks of different colors will be different based on the what type of your target is there. Then you get the information 3 band. Then multispectral band means each channel will have a particular width. So these are the multispectral channels sensors are there, and then comes the hyperspectral sensors. Hyperspectral, very high resolution, spectral resolution sensors. Bottom you can see that information is there. That is one image or particular area is there on this side, front side. But on the other side, one is different spectral bands are there. So these colors you may be seeing yellow, red, and violet. So these are different spectral channels or particular pixel only. Pixel means particular point in the earth, what we are seeing from the different bands, spectral bands. So using those things, we get the different information and different, here we are showing only the colors, so that means the false color composite. But really, if you, for the analysis or classification, we use the actual data because you cannot visualize those things clearly. But this is 3D cube has been shown. But you cannot visualize clearly. So for visualization, you use only the 3 bands, any 3 band, and based on that, you get the, all these information. So hyperspectral are also being used, but these are very complex type of systems are there, as I told, sensor-wise itself, and the data collection and downloading, everything is involved, huge amount. So based on the information, what type of information we want, we get. Yeah, this is one example how you see any particular area in different channels. In blue colors, if you see, ocean is seeing dark, vegetation is dark, cloud is seeing bright, and non-vegetation, that is parent line type of this is seeing bright, snow. So different combinations of the target you are seeing in the one particular band. If you go to another band, the green band, then you see in different way. So those targets are seen in different band. Then in red band, you will see same target in the different way. So that is the purpose of showing only that if you combine these three, this is only example of 3 bands. So one particular image or a phenomena itself, if you see from the different bands or different channels, you can classify those things. That is the purpose. Then anyhow, radiometric resolution I talked about. This is the how you discriminate between the different bitwise. That is 2-bit or the 8-bit or 16-bit data, 12-bit data. The bit anyhow, you all of you, because nowadays computer is everybody is learning. So how we define the bits, 2-bit data or the 8-bit data, and basically it is that as you see, 2-bit you can have the information up to the 4. But if you have the 8-bit data, then information 0 to 255, that is 256, you can have the resolution up to 1, 2, 3 like that. Any information can be up to the, can be 1, 2, 3. But if you have 2-bit data, then information can be only 0, 1, 2, 3 only. So whole information, when you are dividing it only in 2 bits, then the information itself is, many information is lost. So as many more bits you have, that means more radiometric resolution, you can store the information, much more information from the same sensor. Even sensor is same, but information can be, when you are storing, it depends upon what the radiometric resolution is there. Like this, one is a 2-bit versus 8-bit image. Clearly you see the difference between these two. All of the resolutions are same, even then information is degraded. Then temporal resolution, anyhow, I talk about, that is different satellites, how the orbit takes place, and then based on that, you get that 5 day, 10 day, 30 days like that. Okay, so now this also many of you might have read, because this is one of the basic when we go for the remote sensing things. All these laws, like Planck's law, which is basically what deals with the black body. So how, depending upon that, this is just, you don't go much detail. This is the overall brightness, what we call it, or the spectral brightness at particular. Nu is the frequency or the wavelength. H is the Planck constant. Nu is, this is the, as we can see, and all the T is the, here is the, mostly you see the, what is the thing, variables are there, is the brightness, temperature, or B, or spectral brightness, frequency, as well as the temperature. Actual temperature, physical temperature. All other things are constant. C is constant, H is constant. So we play with this based on the frequency at which you are working in passive, even in the active passive, you have receivers, because you don't have any active sensor, but receivers. So receiver at which frequency is there, you are observing, as well as the temperature of the surface, that is Earth surface or the atmosphere, what you want to take information. That accordingly you get the brightness or the energy. So this is overall equation. It is Planck's law follows all these remote sensing instruments, and depending on the what frequency you are working, like very well the low frequency when you are working, this is law is simplified, and then directly it is related to the temperature. The brightest temperature will directly relate to the temperature, like in a microwave. Then for the very high frequency, this law itself you can approximate in different ways. So this is just an example for that. Similarly, for the different law, what we make it based on the Planck's law only. That means at which is the maximum radiation occurs at for particular temperature. I will come upon that. So to tell you that how you get the different energy from the different type of matter in the land. So brightness temperature is, I'll just briefly say, because nothing is a black body. Black body is actually perfect body where everything is absorbed 100%, or what we say, same thing is emitted, 100% emission or 100%. But nothing is a black body. So it will depend upon the emissivity, how much emissivity of particular this epsilon is there, of particular target or particular type of matter is there, and basic temperature, the actual temperature of that. If you multiply that, then you get the brightness temperature what we observe in the satellite, in the passive sensor. This is the brightness temperature we get, not the exact temperature of because in emission what you are having the sensing is the radiation only, that is emitted radiation. So emitted radiation directly you get in the form of the brightness temperature, which is dependent upon the directly on the temperature of the actual what is surface. Yeah, so I was talking about this. You see, for the different type of actual temperature, this is 100 K, 6,000 K to 10 billion K. How at different frequency, what is the maximum radiation will be there? So, like you see around 100 K or 300 K of what Earth temperature, that is Kelvin. That's why you get 300 K. So, at this frequency, around that 10 micron, get the maximum. So, if you have the sensor around this frequency, then you get the maximum radiation, that is maximum energy. Otherwise, if you have the sensor in other regions also, but energy will be less. So total energy will be less. Your detection will be somewhat less. Similarly, for the sun, 6,000 K. So your total energy, as you know, what we see in the visible range only, that is 0.4 to 0.7 micron. But whereas in the